So in terms of the overall design and operation, there's a variety of factors you want to take into consideration when you're selecting a compressor. Um, Perhaps the biggest one is compressor capacity. Essentially, how much fluid will it move? How much air will it move? In terms of the quality of the compressor, you definitely want to look at how long you want it to work, right? There are various qualities compressors out there. A better quality compressor will hopefully have a much longer service life. Obviously, the environment that it's going to run in is going to play a role. The fact is, we have compressors that can handle dirtier environments. We have compressors that are built for higher elevation environments, etc. So you need to look at that temperature, pressure, different types of contaminants, etc. How well your compressor is going to be able to withstand those issues. Uh, Cost always plays a big role in the choice, but keep in mind we're not only talking about the initial cost because we really need to look at the long-term cost, but we also need to look at how much it costs to install these systems. So there is the capital upfront cost, the installation cost, and then an ongoing cost. And in terms of comparing the cost of a pneumatic system, you need to take all of those into consideration. By far the most common type of compressor used is the reciprocating kind that essentially uses a piston or a series of pistons. But keep in mind, we're not just talking about the small home units that you might be familiar with. There are larger versions of that in industrial systems, and then we can even get into these very large central systems like the one shown here, where we essentially have a massive set of pistons and a very large receiver. This might power a number of different devices or even a whole manufacturing environment. Within our reciprocating compressors, we have what is known as single acting compressors and double acting compressors. Let's start with single acting. They're very simple. You see an example here on the right, and essentially why they're considered single acting is they're very much like a single acting cylinder in that they only work in one direction. So essentially, as the piston extends, it compresses that fluid. As it retracts, it pulls in more air, but it doesn't generate any compressed fluid. Now, when you think about single acting, keep in mind you oftentimes will see multiple cylinders involved. So, for example, if you take a look here, you see two cylinders over here on the right. That doesn't mean that it's double acting. There's actually two single acting cylinders, but they're multiple stages. In fact, what happens here is the larger unit pressurizes the fluid up to a certain level, then the air travels to the next unit that then pressurizes it further. Right? You can do this with multiple cylinders, anywhere from 2 up to 8 cylinders, and you can have multiple stages, or you can have multiple cylinders doing the same pressure range. They come in a variety of different configurations. This, for example, is a V configuration. You can actually have them in line, like we showed earlier, where they were essentially lined up right over next to each other. Opposed, where they're directly opposite. We can have W and semi-radial arrangements where they're arranged around a circle. So there are a lot of different setups for multi-cylinder arrangements, depending on how many you have and the complexity of your system. Double acting compressors, on the other hand, essentially work in both directions. And if you take a look here, we have a cylinder compression chamber above. We also have one below. As this cylinder goes up and down, the compression stroke of the upper cylinder is actually the intake stroke of the bottom cylinder, and vice versa. So this is constantly going back and forth, and it's compressing the fluid in both the top and bottom chamber. Now, this is going to double your flow rate, but it's also going to double your amount of work. And of course, it's going to be a somewhat more complex system because you have twice as much things going on. The other thing about it is you're using more energy in a relatively small space, so you're going to have issues with heating. You're also going to have issues with wear and lubrication. So generally, you're rarely going to see these double-acting compressors outside. And the only place you're going to see them is really in big heavy-duty industrial situations where you want it to be in continuous service and get the most essentially energy for your buck. One style of rotary compressors is a vane style or sliding vane style compressor. Take a look here on the right. Very similar to a vane style pump. It uses a rotor, in this case a slotted rotor with a set of vanes in here, and it rotates inside the housing, or what's known as the compression chamber in compressors. As the device rotates, this volume increases, that pulls the fluid in. That's what generates the suction to pull the fluid in, and then as it rotates around, it's going to squeeze back down and push the fluid out. So those volume changes allow you to compress air and move it in a positive displacement way from the inlet to the outlet. Another way of doing this is the screw style or rotary screw style compressor. Essentially, this uses one, two, or three helical screws essentially linked together, and as they move, they're going to push the fluid along the axis. The big benefit of these is since you don't have individual pumping volumes, you essentially have a continuously opening and closing pumping volume, then the flow is going to be continuous. It's going to be consistently moving. And in terms of, if you look at it at the pressure itself, it's going to be much smoother. It's not going to get the pulsating that you tend to get in with pistons and even with vanes to a certain degree. Now, originally these were very expensive and we didn't see them in pneumatic systems, but as manufacturing quality has come up and as the availability of these have come up, the price has come down, and we're seeing more and more of these rotary style compressors. They work very well over a long period of time. They have far fewer moving parts than a piston style, and in terms of a precise manufacturing equipment, their controls and their output is more accurate. Right? A couple different styles we have is the dry and the oil flooded. Dry essentially uses a gear built into it to provide the timing to make sure that the two screw elements mesh together. We also can have oil flooded. Oil flooded actually puts oil in there and one of the screw mechanism drives the other one, but with the oil flood you need to have a built-in separator, oil separator, before the fluid goes out to the system, because you're putting a decent amount of oil, too much oil than what you need down the system. So it's required to separate that oil out. Now let's go back to discuss non-positive displacement compressors, or what we refer to as dynamic compressors. Generally, these are going to be used in any application where you want a lot of air movement, but you're not looking for particularly high pressures. The way they're going to work is they're going to speed the air up to give it kinetic energy, and that kinetic energy is then going to be converted over to potential energy in the form of pressurized fluid or compressed air, our case. One of the most common types is this one right here. It's a centrifugal flow compressor. Essentially, we have the prime mover connected here. We have our impeller. This rotates as the air comes in. It speeds up, and essentially it's thrown into this collector. This is referred to as a volute collector because it's shaped kind of like a scroll or like a horn, and the air is sped up and shot out here at a high velocity. That velocity is then converted over to air pressure as the air moves into the system through the volute collector. Another type of rotary non-positive displacement compressor is an axial flow compressor. This uses a set of rotating blades mounted along a shaft, and they're interlinked within a set of fixed blades. So we have our rotor blades and our fixed blades or stator blades. As the air is inlet, These form a series of fins and increase the pressure. This essentially, if you're having a hard time visualizing it, looks like the compressor portion of a jet engine, where we have a whole series of blades located around the edges, both pointing inward on the stator side and pointing outward on the rotor side. There are relatively large clearances between here, but keep in mind this is a multiple stage system. So this is capable of much higher pressures, because although each one of these individual stages might not make that much of a pressure difference, a small pressure difference plus a small pressure difference, etc., all the way through here can have a much larger pressure difference. Now, this does, though, rely on kinetic energy. It speeds up the air to produce pressure, and essentially it moves it continuously axially. Now, this is a relatively uncommon compressor for small devices, but for large industrial environments where you might use a turbine engine, this is a great way of generating a lot of airflow at relatively high pressure. But it is a pretty complicated device. And as a result, you would only do it in applications where it was, the cost, the initial capital cost up front, was outweighed by the overall cost savings down the road. Another form of rotary compressors is the lobe type compressor, as you see here on the right. These are devices where we have two lobed elements. They're interlinked together with a timing gear. They're designed to move within a housing. The housing is pretty closely fitting, but as you can see, there's a small gap here, and there's actually a small gap all the way around the outside. As a result, they're really not capable of generating very high pressure. They are single stage, right? You don't have multiple stages here. So they're generally actually referred to as blowers, because they're only going to generate somewhere around 20 psi at the maximum. There is definitely, as that pressure goes up, there is a certain amount of slippage or leakage that's going to take place, and so they're not particularly efficient for that. The compressibility of air tends to be problematic for pretty much all of these various compressors, however. The fact is, as the pressure goes up, the volume goes down, so it's very difficult to get a very high pressure out of a system with one pumping cycle. So the solution to this is to have compressors be multi-staged. So for example, we see an inline compressor here. This has actually two pistons. The first piston does the initial pressurizing, and the air comes out of this one, goes into this second piston, and then the second one pressurizes it further. If you're ever wondering which is the first stage and which is the second stage, a dead giveaway is the size of the pistons. Right? If you take a look at the first stage, it's a very large piston. The second stage is a very small piston. The idea is this is low pressure, and as a result, it's high volume. As the pressure goes up, the volume goes down. So to continue this operation, you need a smaller piston here. The other issue from a mechanical standpoint, we want the force being generated by these two pistons to be pretty close to the same to balance out the system. So in this case here, we have low pressure and a big area. In this case, we have high pressure and a small area. And what we're trying to do is keep the forces pretty similar in terms of their overall amount pressing on the system. Now, the idea of multiple staging, you can see it clearly here in this compressor, but it will work with pretty much all of the various compressor designs that we discussed. And in fact, when we talked about the axial compressor just a moment ago, that has multi-stages built right into its design. So we can see these used in a variety of different compressor designs where you have multi-stages. One last thing about it, this is an example of a two-stage compressor, but keep in mind, if you want to go to higher and higher pressures, one of the best ways to do that is to use more and more stages. So you can have 3-stage and 4-stage compressors that keep bringing up the pressure incrementally. A major consideration in selecting a compressor is to have its capacity match the system's. So we want the output of the compressor to be pretty close to what the system is necessary for the system to use, or the system demand. So we need to look at these and come up with a way so we consistently have the right amount of air that we need. Now, there's a bunch of different ways we can do this. We can use, for example, just a bypass valve, and essentially that just bleeds off any extra air we make. We can also actually control the speed of the prime mover. So, for example, we can speed up or slow down the electric motor so we have the right amount of air. That's relatively complex to do. Or if we have a very high-end system, we may have a series of sensors built into where it's a computer-based control, where essentially it is very carefully turning on the system, turning off the system, adjusting things like torque, etc., to make sure that we have the right volume we need consistently. Let's take a look at those various control options. The simplest type of control mechanism is bypass control. In these, we determine what our system's maximum flow rate is, the required or highest demand we're going to have, and we set up our system to supply that demand, and we run it continuously. This works very well when we need that much air, but when the demand drops, we essentially bleed off the extra pressure. We use a pressure relief valve, and essentially it gets to the maximum system pressure, and any additional flow at that point just is dumped back to the atmosphere. Now, historically, this was used a lot, but it is relatively costly to operate because our system's running at max constantly when we don't need it. So generally, we've come up with better systems to improve the overall operating efficiency, such as start and stop control. This is used in a lot of devices, a lot of small portable devices. If you ever used a small pneumatic compressor used in the construction industry, you're probably familiar with start and stop control. These essentially the compressor only runs when the pressure is low enough and fills the tank. When the tank gets the desired pressure, it shuts off. And then pressure is going to drop as you use the air. When it reaches the low setting, it turns back on and fills back up. So this works very nicely when you have intermittent air consumption, like in the construction industry, where you might use a nail gun, then stop, etc., and then the system sort of waits until you need it. But in a industrial environment where you need constant air, this system really tends not to be very effective, because the system itself is going to heat up over time anytime you have continuous use, and the potential for overheating is a possibility. Another way of controlling the output volume is by using inlet valve unloading. This system is normally used with portable devices using internal combustion engines. Internal combustion engines aren't easy to turn on and off, so to avoid that, we essentially run the prime mover at a constant speed, and we control the compressor by opening and closing the inlet valve. Generally, with a piston system, the inlet valve is open as we pull air in. It then closes, and we compress the air and push it out. With inlet valve unloading, once the system hits that maximum pressure, the inlet valve stays open. As a result, the piston cylinder range goes up and down, but no air is moved. And the key thing about it is it reduces the load on the prime mover, because no pressure, no back pressure gets built up. So while there's a certain amount of inefficiency because the prime mover is being operated not doing anything, unlike the bypass system actually generates a lot of high pressure air, and we just dump it. This one avoids that by not generating the high pressure air when it's not needed. Another way we can vary the output is by varying the compressor speed. If you speed up the prime mover or decrease the prime mover, you're going to get less flow. This does require relatively complicated controls and obviously a variable speed motor. This is not often done in small units, but can be done in larger central units. The whole idea of this is to only produce the necessary air for the system. So this is one of the most efficient ways, but it does require the highest level of control. The last of the capacity control methods we're going to look at is varying the output by varying the inlet side of the compressor. Essentially, we run our system at constant speed, but as we change the inlet size, that's going to reduce or increase the output air. This works really well with dynamic or non-positive displacement compressors because they have built-in slip. Keep in mind the clearances inside those compressors are very large, so as you block off the inlet, they essentially spin and move less and less air. But it's far more problematic with positive displacement pumps where you have airtight seals. It's going to generate significant stresses and this option is not particularly energy efficient. It would be problematic with positive displacement pumps. But for non-positive displacement dynamic compressors, this method works relatively well. Last thing I want to talk about is what's the process for actually selecting a compressor? Well, first thing you need to do is figure out how much airflow you need. Right? So you're going to look at what your various tasks are, how that's going to be accomplished with the various cylinders, etc., and use that information to work backwards to develop what flow and pressure is going to be necessary. Now, keep in mind that that's your current system demand, but oftentimes over time the demand may go up. So you want to look at historical data and see what's that increased potential is there, and it's very likely worthwhile to build it into a system, particularly if you're doing something like a central unit where it's designed to be there for a long period of time. You then want to look at which compressor type you're going to use. As I said, by far the most common type is the reciprocating piston arrangement. But if you have very large flows and you potentially want to use a turbine, you might want to talk about the axial flow ones. Or if you're looking for a particularly smooth flow, you might want to use the screw type. So there's some options there. In terms of your prime mover, by far the most common type of prime mover is an electric motor, but if you're in an environment where you don't have access to electricity, an internal combustion engine or gas turbine is a possibility. Or if you're in an environment where you have, for example, steam, steam turbine might be an option in a large industrial environment. So a lot of choices there, but a lot has to do with what you have available. You are going to have to be able to control the volume of air delivered. We just talked about your various options there. That's somewhat tied to the prime mover, tied to the environment, tied to your efficiency requirements. Lastly, I should say, then look at your auxiliary components. Clearly, you're going to need various filters. If you're talking about any kind of high efficiency precision equipment, you're going to need dryers, and you're going to need coolers to get the air in at the right set of properties, right condition. And then last, what type of instrumentation are you going to use? Again, that's tied back to your regulation method. It's also tied to the equipment you have available. If you already have some sort of industrial automation system, you might want to tie it into that. So a bunch of choices there. Each of these is gone into detail in your textbook, and I recommend you definitely look through these and study each of these choices individually. As always, with material in this class, there's additional material in our textbook on the course space online. And if you have any questions, don't hesitate to get in touch with me or post questions on the Q&A discussion forum.